Hi, and welcome to this video on the emission spectrum of hydrogen and the Bohr model. In this video, I'm going to discuss what an emission spectrum is. I'm also going to show the difference between a line spectrum and a continuous spectrum. And finally, I'm going to show you how the line emission spectrum of hydrogen is related to energy transitions of the electron in the atom. And to start, let's talk about what atoms do when they get excited. So atoms or molecules, when they absorb energy, either in the form of heat or light or electricity, the energy is usually re-emitted as light. And this phenomena is directly responsible for the glow of a neon sign, for example, and the colors that you see when fireworks occur. Now, just like the photoelectric effect that I talked about in a previous video, this emission of light is another phenomena that can only be explained fully by a particle theory of light and not by a wave theory of light. And we'll see why this is in a few moments. But to begin, let's talk about what exactly is an emission spectra. So an emission spectra is the range of individual wavelengths that compose a sample of radiation that's being emitted by some source. And as an example, we can take a hydrogen discharge tube. Now all this is just a tube that contains hydrogen gas. And when you run electricity through the hydrogen gas, it causes the hydrogen gas to start to glow and give off light. Now if we take the light that's being emitted by this hydrogen discharge tube, and if we run it through a slit, and then if we run it through a prism and separate the light into individual component wavelengths, we would get what is called an emission spectrum. Now there are different types of emission spectra depending on the type of radiation source. The first type of spectra is what we get when we take the light coming from the sun and we run it through a prism. So if we were to take sunlight and run it through a prism, the type of spectrum that we would get is called a continuous spectrum. Now in a continuous spectrum, all of the wavelengths of light are being emitted by the source. And so here we get a rainbow effect. Now this is a much different spectrum than if we take a look at the spectrum that's being emitted by glowing hydrogen. Now if we take the light coming from the hydrogen, and if we run it through a prism, rather than getting this rainbow effect, what we get instead is called a line spectrum. Now notice how the line spectrum of the hydrogen is much different than the continuous spectrum that you would get from the sun. Notice that in the line spectrum, you only have certain discrete wavelengths of light being emitted by the glowing hydrogen. So the question comes up, why is this happening? Why are only certain wavelengths of light being emitted by the glowing hydrogen, whereas other wavelengths of light are not being shown? And the answer to this is connected to a particle theory of light. Now the first person to actually try to describe this phenomena of the line emission spectrum of hydrogen was Niels Bohr. And in 1913, Niels Bohr expanded upon the Rutherford model of the atom, and he tried to explain why hydrogen emits the specific lines that it does. And to give a summary of his model, what he proposed is that electrons reside in these discrete energy levels that orbit around the nucleus. And he also stated that the energy of the electrons are quantized and they can only have certain values, and that the light being emitted by the hydrogen is due to photons being released when electrons are going from a high energy level to a lower energy level. But let's take a look at this model step by step in greater detail. So when we talk about the Bohr model, we have our nucleus. Now in the case of the hydrogen atom, the nucleus only contains one proton. And around that nucleus we have the electron, the single electron of the hydrogen atom. Now according to the Bohr model, this electron resides in a circular orbit around the nucleus. And this orbit, or this energy level, is being designated by a value of n. In this case it's n equal 1. There's a second energy level called n equals 2. It's larger than the first energy level, it's a larger orbit. And then there's a third energy level, a fourth energy level, fifth, sixth, etc. And theoretically these energy levels go to infinity. And when an electron is in an energy level, it has a certain amount of energy. Now the energy of an electron when it's in a given energy level is given by the following equation. E sub n equals negative b over n squared. Now in this case b is a constant, it's called the Bohr constant, and it has a value of 2.179 times 10 to the minus 18 joules. And n represents the value of the energy level. And notice that these values have to be integers. They have to be whole number values of 1, 2, 3, 4, etc. So what we see is that when the electron is in the first energy level, and if we plug our values into the equation, we see that the electron has an energy of negative 2.179 times 10 to the minus 18 joules. Now the reason why it's a negative amount of energy is because this is the potential energy between the negative charge of the electron and the positive charge of the proton. So since it's attraction, it's a negative sign. Now what if the electron's in the second energy level? Then it's going to have an energy value of negative 5.447 times 10 to the minus 19 joules. So it's a lower amount of energy. In the third energy level, we see that the electron has an energy of negative 2.421 10 to the minus 19 joules. And in the fourth energy level, it has an energy value of negative 1.362 times 10 to the minus 19 joules, and so on. So you can figure out the energy of an electron just by knowing the value of n. Now one thing I want to point out here is that when the electron is in the lowest energy level possible, we call this the ground state. Whereas when the electron is in anything but the ground state, we refer to these as the excited states of the atom, or the excited states of the electron. And what we can see in this Bohr model is that the energy of the electron is quantized, and it can only occur in certain discrete amounts, based off of what energy level it's in. So in other words, since an electron cannot be between energy levels, it can only be in one energy level or another energy level, that means that the energy of the electron can only be certain discrete amounts. It can't be a continuous value. Now another thing that the Bohr model talks about is the fact that the electron can undergo transitions, and these transitions between energy states is what's responsible for the emission spectrum and the absorption spectrum of a certain element. So in this model, the electron can be promoted to a higher energy level by absorbing energy. Now it's going to be absorbing energy as a photon of light. So let's imagine the following scenario, where we have a photon of light. Now this photon of light has an energy that's due to its frequency or its wavelength. And in a previous video, I discussed how to calculate the energy of a photon knowing either its wavelength or frequency. And we can imagine this photon of light being absorbed by the electron in its ground state. Now since the electron has now absorbed some energy, it's going to now be promoted to a higher energy state. Notice that the electron went through a transition from an initial state of n equals 1 to a final state of n equals 5. And it went from one energy level to another energy level, and therefore there's a difference in energy between these two energy states. And the size of this energy difference is exactly equal to the energy of the photon that was absorbed by the electron. So now what we're seeing is that when the atom is absorbing photons, it's promoting electrons from a low energy state to higher energy states. Now we can also talk about what happens when electrons are already in an excited state. So electrons in an excited state can drop down to lower energy levels by emitting energy, and they emit the energy as photons of light. So let's think about an electron already promoted to the fifth energy level. So it's an excited state electron. And let's say that it drops back down to a lower energy state. As it drops back down, it emits a photon. Now the energy of the photon is still being given by Planck's constant times frequency, or hc over lambda. But in this case, we went from an electron transition from a high state of n equals 5 to a lower energy level of n equals 1. But just like before, the energy gap that's being traversed by the electron is exactly equal to the energy of the photon, except that this time the photon is being emitted because the electron is going from a high state to a low state. So now what we can do is, if you recall, we were able to figure out the energy of an electron when it's in a given energy level. However, we can also now use this relationship to derive an expression that allows us to calculate the change in energy between any two energy states. And this delta E, this change in energy, is given by the following expression, negative B times 1 over nf squared minus 1 over ni squared. Now this expression has nf, which is the final energy level, and ni is the initial energy level of the electron. And what we can see is that since the change in energy between the two energy levels is exactly equal to the energy of the photon associated with the transition, we can also come up with another expression that says that E photon is equal to negative B 1 over nf squared minus 1 over ni squared. And since we know the energy of the photon is related to its frequency or wavelength, we now have a relationship that shows what wavelengths of light will be emitted when certain electron transitions occur in the hydrogen atom. Now these equations here give us a mathematical understanding of what's actually going on with the emission spectrum of hydrogen. And they're very important, and you're going to have to be able to do calculations based off of them. And anytime you do calculations with these equations, we need to start paying attention to the sign of delta E and the sign of E photon, because the sign is going to tell us whether photons are being emitted by the process or being absorbed by the process. So when you do these calculations, if the sign of delta E or if the sign of E photon is positive, that means that a photon is being absorbed by the electron and that the electron is going from a low energy level and ending in a higher energy state. Whereas when the sign of delta E is negative, that means that photons are being emitted or released and electrons are going from a high energy state and ending in a low energy level. So the sign of delta E is going to be really important for us establishing whether photons are being absorbed or emitted by the process. Now we can finally understand why the emission spectrum of hydrogen only has certain discrete wavelengths being emitted. When the electron starts off in the 6th energy level, and if it transitions down to the 2nd energy level, a photon of light is being emitted that has a wavelength of 410 nanometers. And that's this first line in the emission spectrum of hydrogen. For the second line, we have an electron transition that occurs where the electron starts off in the 5th energy level and drops down to the 2nd energy level. It emits a photon of light having a wavelength of 434 nanometers, which is the second visible line. Now the third visible line is due to a transition where the electron starts off in the 4th energy level and then drops down to the 2nd energy level and emits a photon having a wavelength of 486 nanometers, which is the third spectrum line here. And then finally, the fourth spectrum line is due to the emission when the electron starts off in the 3rd energy level and drops down to the 2nd energy level and emits a photon having a wavelength of 657 nanometers. Now recognize that these 4 lines are the visible lines of the spectrum. These are wavelengths of visible light. However, there are many more lines in the spectrum that are due to infrared and ultraviolet radiation. So for example, the infrared radiation are due to these transitions here, whereas the ultraviolet radiation is being emitted by these transitions. Again though, notice that there are only certain discrete transitions that can occur in the hydrogen atom, so therefore there are only going to be certain discrete wavelengths of light being emitted by the electron. And now we know why there's a line spectrum that's being emitted by the hydrogen rather than a continuous spectrum. And it's all because of the discrete nature of the electron transitions and the energy levels. Now the Bohr model is good, but it's not perfect, and there are some limitations that you should be made aware of. The first problem is that the electron does not orbit the nucleus like a planet orbiting the sun. And in fact, we're going to find out in future videos that it's impossible for us to have this much knowledge about the position of an electron with such certainty. Another issue with this model is that the Bohr equation can only predict the line spectrum of one electron systems. So the hydrogen atom or the helium cation or the lithium 2+ cation, these are systems that have only one electron to them. And therefore the Bohr model is sufficient and the Bohr equation is able to calculate the line spectrum of these systems only. But when you start having systems that have more than one electron, the Bohr equation is not able to predict the line spectrum. However, the Bohr model was totally correct in that electrons reside in discrete energy levels. So he was totally correct on this. It was also good for explaining that the fact that energies of electrons can be quantized and can only occur in certain discrete values. Now, even though Bohr's model was not perfect, it was an important step to the formulation of a more complete theory of quantum mechanics, in which we start talking about the wave nature of electrons. But this is a topic for another video. Okay, so now that you've watched this video, you should first pat yourself on the back and take a break. But after you take your break, you should be able to explain the line emission spectrum of hydrogen using the Bohr model of the atom. You should also be able to do calculations based on the Bohr model, and you should be able to identify the model's strengths and weaknesses. Okay, so that's it for now. I'll see you in a future video. Bye.